Motors are used everywhere in our homes and businesses. To get a motor started, it must overcome friction and the connected load. Motor starting currents, usually called inrush currents, are very high, on the order of 6 to 8 times the normal operating or rated current. When this current is pulled through the impedance of a power system, voltage drops. The size of the motor and the impedance or resistance to current flow of the system dictate how much the voltage will drop. Consequently, voltage drops can lead to simple issues like light flicker, or more complicated and problematic situations like critical equipment shutting down. Depending on the problem and the cost or circumstances associated with the voltage issues, various motor starting techniques are used to avoid issues and prevent downtime or other situations. There are 3 types of motor starting methods, and each has an effect on inrush current and the associated voltage drop. Across the line, or ATL, soft starting, also called reduced voltage starting, and variable frequency drives, or VFDs. Once the motor is started, VFDs can offer significant operating benefits as well, including speed control and energy savings. In this video, we'll cover considerations, risks, and cost benefits of each method. Let's start with a simple explanation of each. An across-the-line motor starter simply connects the motor to the source voltage with a contactor, like a light switch turning on a light. If you were driving a car, an ATL starter would be like slamming the gas pedal to the floor. An ATL motor starter uses an overload system that will trip the contactor before the motor would be damaged if something significant happens to the load, like a locked rotor condition, or simply if you try to drive too much load with the motor. The ATL motor starter has to work with a fuse or breaker to trip during fault conditions. This pairing of a motor contactor, overload, and a fault protection device is often called a combination motor starter. To turn off the motor, you trip the contactor via a switch or other control method. Depending on the overload relay and protective device associated with the ATL starter, it is often significantly less expensive than the other 2 methods of motor starting. Therefore, it's the most common method and usually the preferred method for small motors. With larger motors, 25 horsepower or larger for example, soft starters or VFDs are typically standard practice. Soft starters reduce the inrush current of the motor by pulsing the voltage on with power electronics, usually SCRs, ramping the RMS level from 0 volts to full voltage. Using the light analogy, this would be like adjusting a dimmer from off to full on and then leaving the light on at full output. The soft start would be like slowly accelerating your car with a gas pedal, pushing it all the way to the floor and then driving your car at full speed. With a soft starter, the motor draws significantly less current during starting, on the order of 1.5 to 3 times nominal current instead of 6 to 8 times. This minimizes the voltage drop issues and is programmable across the range of starting times. Usually, the longer it takes, the less current you'll draw. Once the motor's overcome inrush and it's operating at full speed, the soft starter will automatically transfer across the line with the bypass contactor. This allows the motor to operate at nominal 60 Hz speed after it's up and running. To turn off the motor, you simply trip the bypass contactor. Like the ATL starter, the soft starter needs a partnering device to handle fault currents, so it pairs up with a fuse or a breaker. The soft starter is more gentle on the motor and therefore can have a financial benefit over the standard ATL motor starter from a motor maintenance standpoint. One important point to understand is that soft starters do not save demand charges on your utility bill because those demand charges are averaged over 15 minutes and motor starters only take a few seconds. This is a common misconception to be aware of. There are several key settings on a soft starter, and it's important to understand how those settings affect the starting time and the inrush current. Finally, a variable frequency drive offers a more refined soft starting capability as well as the opportunity to control the speed of the motor after starting. Using the light dimmer analogy, you could change the light from off to any output level and then leave it there without going to full output power. With the vehicle analogy, you could slowly adjust your speed from a stop to any speed and then stay there, and beyond that, you could readjust your speed or even slow down to a stop. Controlling the starting, stopping, and running of a motor are completely adjustable with a variable frequency drive. Although the cost of the VFD is the highest of the 3, It offers other benefits, namely full control below and above nominal frequency range, power factor correction on the input of the drive, internal protection against overloads and faults with current limiting capability, and most importantly, energy savings when operating below the nominal frequency. VFDs and soft starters produce harmonic currents during starting of the motor. VFDs also produce harmonics during normal operation. In both cases, harmonics should be considered from a system standpoint to make sure these currents don't corrupt the voltage and interact with power factor correction capacitors on the system. Many people recognize the existence of harmonics from a VFD, but often do not recognize that they're also produced with soft starters. This is usually only a resonance problem and not a long-term heating problem, since the harmonics only exist for a few seconds that it takes to start the motor. The advantages and disadvantages of each motor starting and control technique are summarized in this table. Beyond their benefits for motor starting, VFDs can offer significant energy savings depending on the application. In general, the energy savings are a cubic function proportional to the speed. For example, if you operate at 50% speed or 30 Hz on a 60 Hz system, the motor would only use a half times a half times a half, or 1/8 of the power required to run the same motor if you constricted the flow mechanically. If you use an across-the-line motor starter or soft starter, you would have to use dampers on an airflow system or valves on fluid systems to restrict the flow mechanically. From our vehicle example, this is like driving with your foot all the way to the floor on the gas pedal and controlling your speed with the brake. It's horribly inefficient. Now, one thing that's extremely important to understand is that you would never buy a VFD and use it only as a soft starter. I'll repeat that. Don't use a VFD only as a soft starter. Why? Well, don't forget that a variable frequency drive converts the frequency by first taking the AC input and converting to DC with a rectifier, and then it converts it back to AC with an inverter. These two converters have losses, which means that if you operate at 60 Hz, you would pay for those losses all day, every day. But if you're using a VFD as intended to change the frequency or speed of the motor, you will see all the benefits that we mentioned previously, including energy savings, speed control, and soft starting. Selecting one method of motor starting and operation over another is often first a cost thing and second a control thing. But in many cases, these situations are related, and if full control is required, a VFD is probably the right option. Many of the demonstrations we have at the Power Systems Experience Centers show the benefits of using each of these starting and control methods. And like most of our demos, we can show a good, better, best version of each. If you'd like to learn more about motor starting and control, contact us or your local Eaton representative to schedule a visit to one of Eaton's Power Systems Experience Centers today.